when we're looking at a scatter plot or a plot of XY ordered pairs, we can also calculate something called the correlation coefficient, which just measures the strength of a linear pattern in a set of data. Now, the correlation coefficient is calculated using this formula. So n is the number of data points you have in your sample. Sigma xy is the product of the xy ordered pairs, and then the sum of those, right? Minus the sum of the x's times the sum of the y's. And in the denominator, you have these terms, which are the square roots of the sample size, times the sum of the x squared terms, minus the sum of the x terms, and take that sum and raise it to the second power, times, and then sort of the same calculation with the y values. Now, what this does is creates a number that has to lie between -1 and +1. As the correlation coefficient r is closer to one of those extremes, -1 or +1, the points demonstrate a more clear or stronger linear pattern. As it goes towards the center of that range, or 0, there's little to no pattern, or little to no linear pattern in the data. Although there could be a clear pattern, it's just not a straight line pattern. So here are some examples. So in this case, figure 21, in this first graph, we see that the points look like they're on a straight line. So r would either be 1 or very close to +1. If you have an increasing trend, so as x gets bigger, so as you move to the right, y also gets bigger or gets farther towards the top of the graph, or it moves up the y-axis, then that's going to have a positive slope, and r will match and have a positive value. Now, in the second figure, you see that there's a negative slope, so the line goes down as x gets bigger, y gets smaller. So r is going to be negative, and since the points are either on a straight line or very close to it, we would expect r to be very close to -1. So in the first graph, r could be 1, or it may be something like +0.958 or something. It really depends on the scale of x and y. In the second graph, r is going to be close to -1, but in this case, the magnitude is close to 1, but the sign is negative. So r may be -1, or it may be -0.999. Now in the third graph, you can see a clear linear pattern. And you would remember from previous math work that this would be like a parabola, or a second order equation in x. But in this case, it's not linear, so r actually turns out to be close to 0. It doesn't mean that there's not a relationship between x and y. It just means that there's not a straight line or a linear relationship between x and y. In the last graph, again, you see a circular pattern. There's a clear pattern that exists, okay? But what happens is it's not linear. So again, r is close to 0. Now in terms of calculating r, what we would do is go back and we can find our values for the sum of the x's, sum of y's, sum of the xy pairs, sum of the x squared terms, and some of the y squared terms from the table we looked at earlier. Then what we would do, along with the sample size of n equal to 10 data points, is substitute those numbers into the equation. And they've done a nice job of color coding everything, so it's easy to figure out where all the numbers go. So you should be able to plug in each of the values into this equation, do the arithmetic, and come out with a correlation coefficient of about -0.963. Because the number part is close to 1, 0.963 is only 0.037 away from 1. Okay, so it's just the number part. That tells me that the points are very close to a straight line. Okay, they're not exactly a straight line because I would have to have 1 for the correlation coefficient for the points to be collinear, or to fall exactly on a straight line. But they're very close. The negative tells me there's a decreasing trend. So what that means is that as x gets bigger, y gets smaller. And that was definitely the pattern that we saw in the graph of the data points when we were looking at this back on page 26. So that's an example of how you can use the correlation coefficient to sort of gauge how strong of a linear pattern exists in your data set.